Welcome back to the Chromperfect Chromatography Theory series. In the previous two videos, we examined SEC integration and SEC calibration. We considered the special baseline used for size exclusion chromatography, the influence of detector-response, the calculation of molecular weight averages and fractions, the construction of SEC calibration curves, universal calibration, viscosity relationships, and the use of narrow and broad molecular weight standards. In this video, we will move into advanced SEC theory. These subjects are intended for serious SEC chromatographers. They build upon the principles already discussed and examine how molecular weight distribution plots should be interpreted, how chromatographic broadening affects calculated results, how axial correction attempts to compensate for that broadening, and how advanced SEC information can support preparative fractionation and the characterization of broad standards. We will begin with the interpretation of SEC molecular weight distribution plots. Interpreting SEC molecular weight distribution plots. A Chromperfect SEC molecular weight distribution plot can display a large amount of information. Depending upon the selected settings, as many as 10 traces may be shown. This complexity can make the plot appear difficult to interpret. However, several fixed relationships exist among the traces, their peak positions, and the molecular weight markers. Understanding those relationships makes the complete plot much easier to read. The basic idealized example. We will begin with an idealized chromatogram. Assume that the chromatogram consists of one broad, symmetrical Gaussian peak with no detector noise. Assume that the chromatogram was collected using a refractive index detector or another mass-sensitive detector. We will also assume that the SEC calibration curve is linear and that axial correction is not being applied. These assumptions deliberately remove the complications that will be introduced later. For this example, the calibration curve is selected so that the midpoint of the SEC processing range corresponds to a molecular weight of 100,000 Daltons. The complete processing range covers slightly more than 2 decades of molecular weight. The original chromatographic peak is symmetrical within the processing range, and the peak top corresponds to 100,000 Daltons. When this chromatogram is converted into an SEC molecular weight distribution plot, the weight fraction trace closely resembles the original chromatogram. The axes and scales are different because the horizontal axis now represents molecular weight rather than time, but the profile remains Gaussian. Because the calibration curve was selected carefully, the weight fraction peak remains near the center of the plot. The cumulative weight fraction trace represents the integral of the weight fraction trace. It is normalized so that it begins at 0 and ends at 1, or from 0 to 100% when expressed as a percentage. At any molecular weight, the cumulative trace indicates the proportion of the sample that has already been accounted for on one side of that point. For a symmetrical Gaussian distribution, the halfway position on the cumulative trace lies below the peak top, as expected. The number and weight average markers. The molecular weight distribution plot may also display markers for the calculated molecular weight averages. The MN marker indicates the number average molecular weight. The MW marker indicates the weight average molecular weight. For the idealized Gaussian distribution, Mn lies slightly to the low molecular weight side of the peak top. On a conventional SEC plot, where high molecular weight appears on the left and low molecular weight on the right, the Mn marker is therefore positioned slightly to the right of the peak top. This occurs because the low molecular weight side contains a larger number of individual molecules. Mw lies slightly to the high molecular weight side and is therefore positioned to the left of the peak top. This occurs because the more massive molecules have greater influence upon the weight average. The distance between the Mn and Mw markers is related to the logarithm of the sample's polydispersity. A narrow distribution produces markers that are close together. A broader distribution produces markers that are farther apart. The same effect can be observed when the slope of the SEC calibration curve changes. A calibration curve that converts a small time difference into a large molecular weight difference will increase the apparent spacing of the molecular weight averages. The marker spacing must therefore be interpreted in the context of both the chromatographic width and the calibration curve slope. The other molecular weight distribution fractions. The molecular weight distribution plot can display several fraction traces. The principal traces are the number fraction, the weight fraction, the z fraction, and the z+1 fraction. For the idealized chromatogram and linear calibration curve, these four traces share several regular characteristics. All four traces remain Gaussian. They have the same height and width. However, they are displaced from one another along the molecular weight axis. From the low molecular weight side toward the high molecular weight side, the order is number fraction, weight fraction, z fraction, and z+1 fraction. The spacing between adjacent traces is equal to the spacing between adjacent molecular weight average markers. The molecular weight markers occur at the intersections of the fraction traces. The MN marker is located where the number fraction and weight fraction traces intersect. The MW marker is located where the weight fraction and z fraction traces intersect. The MZ marker is located where the z fraction and z+1 fraction traces intersect. The MZ+1 marker does not have an equivalent final intersection because there is no z+2 fraction trace. These relationships provide a useful visual check. Even when the traces become more complicated, the order of the traces and the relationship between the markers and trace intersections should generally remain recognizable. Why the weight fraction trace matches the original chromatogram. In this example, only the weight fraction trace has its peak top in the same location as the original chromatographic peak. That is not an inherent property of every SEC analysis. It results from the assumption that the original chromatogram was obtained using a mass-sensitive detector. The detector-response type declared in the SEC calibration file determines which molecular weight distribution trace corresponds directly to the measured chromatogram. With a mass-sensitive detector, the original response corresponds to weight fraction. With a mole-sensitive detector, the number fraction trace would correspond more directly to the original chromatogram. With a Z-sensitive detector, such as the idealized response of a low-angle light scattering detector, the Z fraction trace would occupy that distinguished position. Correct declaration of detector type is therefore necessary not only for the numerical calculations, but also for correct interpretation of the plot. The viscosity fraction and Mv. So far, we have considered the number, weight, z, and z+1 fractions. The viscosity fraction and the viscosity average molecular weight, Mv, add another trace and another marker. Their positions depend upon the Houwink exponent, alpha. When alpha equals 0, the viscosity fraction and weight fraction traces are superimposed. Under that condition, Mv is not physically meaningful as a separate viscosity average, and Chromperfect reports it as equal to Mw. When alpha lies between 0 and 1, the viscosity fraction trace lies between the weight fraction and z fraction traces. As alpha approaches 1, it moves toward the z fraction trace. When alpha equals 1, the viscosity fraction and z fraction traces are superimposed. When alpha lies between 1 and 2, the viscosity fraction trace lies between the z fraction and z+1 fraction traces. When alpha equals 2, it becomes superimposed upon the z+1 fraction trace. The Mv marker always occurs at the intersection of the weight fraction and viscosity fraction traces. When alpha is close to 0, Mv lies approximately halfway between Mn and Mw. As alpha increases, Mv moves toward the high molecular weight side. It passes Mw as alpha passes through 1. When alpha equals 2, MV lies approximately halfway between MW and MZ. This behavior demonstrates that the viscosity average molecular weight cannot be interpreted independently of the applicable Mark-Houwink relationship. Real chromatograms. The idealized Gaussian example provides a clear framework, but real chromatograms are more complicated. Consider a chromatogram containing 3 broad, overlapping Gaussian peaks, together with a small amount of random detector noise. When this chromatogram is converted into number, weight, Z, and Z+1 fraction traces, the traces no longer have identical shapes, heights, or widths. The weight fraction trace still reproduces the shape of the original chromatogram because the detector is assumed to be mass-sensitive. The other traces apply different molecular weight weighting. The number fraction trace emphasizes the later, low molecular weight portion of the chromatogram because that region contains a larger number of individual molecules. In the 3-peak example, the later overlapping peak becomes more prominent in the number fraction trace. The Z fraction trace emphasizes the earlier, high molecular weight region. The Z+1 fraction trace emphasizes this region even more strongly because it applies a still higher molecular weight weighting. The molecular weight markers are also farther apart than in the simple example, reflecting greater polydispersity. They are no longer equally spaced because the chromatographic distribution is not a single Gaussian peak, and the relationship among the weighted averages is no longer uniform. Nevertheless, the order remains the same. The number-related quantities lie toward the low molecular weight side, and the increasingly weighted averages move progressively toward the high molecular weight side. The marker intersections also remain meaningful. The molecular weight markers should still appear at the intersections of the corresponding traces, except for MZ+1, for which there is no higher order trace. The effect of noise on the different traces. Detector noise appears in the molecular weight distribution plot, but it does not affect every trace in the same way. The weight fraction trace reproduces the detector noise directly when the original detector is mass-sensitive. The number fraction trace gives additional emphasis to response on the low molecular weight side. Consequently, low-level noise near the late end of the chromatogram may become more prominent. The Z and Z+1 traces strongly weight the high molecular weight region. Noise near the early end of the chromatogram may therefore become much more prominent in those traces. This behavior is important because apparently small baseline fluctuations can exert a disproportionate influence upon higher molecular weight averages. The presence and location of noise should therefore be considered whenever the fraction traces or molecular weight markers appear irregular. Axial broadening. Up to this point, we have assumed ideal chromatographic conditions. Under ideal conditions, the sample would be introduced in an infinitesimally small volume, and the column would separate molecules according to molecular size without adding any additional spreading. Real SEC chromatograms can approach that condition, but can never fully attain it. The injected sample occupies a finite volume. Connections, tubing, detector cells, and other extra column volumes contribute broadening. Within the column, diffusion and mass transfer effects spread material along the direction of flow. This longitudinal spreading is commonly described as axial broadening. The observed molecular weight distribution is therefore broader than the true distribution entering the column. The relationship can be represented conceptually using variances. The square of the observed distribution width is the sum of the square of the true sample distribution width and the square of the chromatographic broadening. For Gaussian distributions, this can be expressed using standard deviations. Sigma observed squared equals sigma sample squared plus sigma column squared. Sigma column represents the broadening introduced by the chromatographic system. In Chromperfect, the column sigma value is expressed in time or volume units. A perfectly monodispersed standard has no genuine molecular weight distribution width. However, when it is chromatographed, it still produces a peak with finite width. Under the model, that observed peak width represents column broadening. A broad polymer has its own genuine distribution width, and the column broadening is superimposed upon it. The result is an observed chromatogram that exaggerates the breadth of the original molecular weight distribution. Consequences of axial broadening. Axial broadening affects several calculated quantities. It increases the apparent polydispersity. It moves Mn toward the low molecular weight side and Mw toward the high molecular weight side. Higher order averages can be affected even more strongly because they emphasize the extreme high molecular weight region. Broadening also mixes material between neighboring apparent fractions. A fraction collected at one elution time does not contain only material whose true elution position corresponds exactly to that time. It contains contributions from molecules whose ideal positions lie on either side. This contamination is especially important in preparative SEC and in broad standard calibration. The ordinary SEC calculation assigns one molecular weight to each chromatographic data point using the calibration curve under axial correction. Under axial correction, each observed data point is instead treated as a mixture of contributions from neighboring ideal positions. The amount assumed to leak from a neighboring point depends upon two factors. It depends upon the amount of material at that neighboring point, and it depends upon the distance between the points. The distance weighting is modeled as a Gaussian distribution with a standard deviation equal to the column sigma value. These weighted neighboring contributions and their uncorrected molecular weights are then used to calculate corrected molecular weight averages for each observed point. The process does not reconstruct an exact original chromatogram. It applies a mathematical model intended to estimate the molecular weight distribution that would have been observed with less chromatographic broadening. Assumptions and limitations of axial correction. The correction depends upon several assumptions. The broadening is assumed to be Gaussian. The column sigma value is assumed to describe the complete chromatographic system adequately. In some applications, broadening is treated as independent of elution time. In reality, broadening may change across the separation range. It may depend upon molecular size, flow rate, diffusion coefficient, column condition, injection volume, and extra column effects. A single column sigma value is therefore an approximation. If the value is too small, the correction will have little effect. The corrected molecular weight estimates will remain close to the ordinary calibration curve. If the value is too large, the correction may become physically unrealistic. An excessive column sigma value can imply that the chromatographic broadening is greater than the observed peak width. It may produce calculated molecular weight traces with a positive slope, which is physically impossible for a conventional SEC calibration, where molecular weight must decrease with increasing elution time. Axial correction is also sensitive to noise. The calculation uses neighboring detector responses and high powers of molecular weight. Noise near the baseline can therefore create unstable corrected estimates, particularly at the ends of a peak. Smoothing and a suitable noise threshold can reduce these effects. But they must be used without excluding genuine distribution tails or distorting the chromatogram. Axial correction should consequently be regarded as a model-based estimate, not as a direct measurement of the true, unbridled distribution. Calculated molecular weight SEC calibration plots. The SEC calibration file editor can display the calibration curves stored in a SEC calibration file. However, because no raw data file or bound file is associated with the editor, it cannot display corrected molecular weight values calculated from an actual chromatogram. This limitation is removed in the analysis program and in formatted reports. When the SEC calibration file specifies that axial correction should be applied to samples, a SEC calibration plot can display calculated molecular weight averages for each chromatographic data point. A typical plot may show the original calibration curve together with the calculated sample, Mn, Mw, Mz, or other molecular weight average traces. Not every chromatographic data point is necessarily displayed. Only points within the SEC processing range are included. Points below the SEC noise threshold are excluded. For that reason, the calculated trace may contain gaps or discontinuities. The calibration curve itself is smooth and continuous. The calculated molecular weight traces are commonly irregular or jittery, particularly near the ends of the chromatographic distribution. Near the baseline, detector noise becomes large relative to the genuine analyte response. The axial correction algorithm interprets that noisy response while considering neighboring points, producing unstable corrected values. Increasing the SEC noise threshold can suppress some of these regions. Smoothing the chromatogram may also improve the calculated traces. However, raising the threshold excludes more of the molecular weight distribution tails, while excessive smoothing changes the chromatographic profile. The analyst must balance noise rejection against preservation of genuine low-level material. Why the corrected MW trace follows the chromatogram? The calculated sample MW trace typically weaves above and below the ordinary calibration curve. Its movement reflects the slope of the original chromatographic profile. Where the chromatogram is rising, the observed fraction receives more leakage from later eluting material than from earlier eluting material. Later eluting material has lower molecular weight. The corrected average is therefore shifted downward toward lower molecular weight. Where the chromatogram is falling, the fraction receives proportionally more leakage from earlier eluting material. Earlier eluting material has higher molecular weight. The corrected average is therefore shifted upward toward higher molecular weight. The corrected trace, consequently, follows a pattern related to the shape and slope of the original chromatogram. This is not random behavior. It is the expected result of the neighboring point contamination model. Local polydispersity. The calculated Mn and Mw traces can also provide information about the polydispersity of individual chromatographic fractions. Where Mn and Mw are nearly coincident, the local fraction is relatively narrow. Where the two traces separate, the local polydispersity is greater. The ratio of the local Mw to local Mn provides a local polydispersity index. In regions near a chromatographic peak top, there is relatively little contamination from material on either side. The local fraction may therefore appear comparatively monodisperse. In a valley between two overlapping distributions, material leaks from both sides. The local fraction can contain molecules from two substantially different molecular weight regions. Its calculated polydispersity is therefore higher. This information can be valuable in preparative sec because it helps identify where fractions should be cut. A cut near a local minimum in polydispersity may produce a narrower fraction. A cut through a region of high local polydispersity may collect a mixture of neighboring distributions. Validating the column sigma value. Calculated molecular weight traces can also help evaluate the selected column sigma value. When the value is too small, the calculated averages become nearly indistinguishable from the ordinary calibration curve. The correction has little practical effect. When the value is too large, the corrected traces can show physically impossible behavior, including a positive molecular weight slope. This indicates that the model is attributing more width to column broadening than is present in the observed distribution. The analyst can therefore compare the calculated traces with the calibration curve and chromatogram when assessing whether the selected column sigma value is plausible. Noise and numerical resolution. The axial correction calculation is sensitive not only to detector noise, but also to numerical roundoff. The algorithm may involve extremely large molecular weight powers and small differences among weighted sums. All digital calculations have finite precision. In normal applications, the resulting deviations are usually negligible, but they can become visible in extreme examples. Consider an ordinary broad Gaussian chromatographic peak with a small amount of detector noise. Now, assume deliberately that the column sigma value is set equal to the observed peak width. The correction model will treat the complete observed width as chromatographic broadening. It will therefore infer that the true sample distribution has zero width and is monodisperse. The calculated molecular weight average traces should become horizontal and overlap. The molecular weight distribution traces should also overlap, and all molecular weight markers should appear at the same position. In practice, they may not be perfectly identical. Noise in the chromatogram creates small differences in the calculated values. Near the peak ends, those differences are more obvious because the genuine detector response is weak. Even near the peak center, small discrepancies can remain. The markers may not occur in the ideal order, and they may fail to lie exactly at the expected trace intersections. These apparent failures may look serious when the plot is highly expanded, but their magnitude must be compared with the resolution of the acquired data. Molecular weight resolution per data point. The sampling interval and calibration curve slope place a fundamental limit upon the molecular weight resolution of the data. The change in logarithmic molecular weight per acquired data point equals the calibration curve slope multiplied by the sampling interval. The corresponding fractional molecular weight change is derived from that logarithmic difference. If successive data points differ by 0.3% in molecular weight, the acquisition cannot reliably distinguish calculated values separated by much less than that amount. Increasing the sampling rate can improve this resolution to a limited degree, because the time interval between points becomes smaller. However, oversampling cannot recover information that has already been lost through chromatographic broadening, detector noise, or inadequate separation. Higher-order averages such as Mz and Mz plus 1 are also more susceptible to round-off error because they use higher powers of molecular weight. When evaluating an apparently monodisperse material, Mn and Mw generally provide a more stable assessment. A calculated polydispersity close to 1 should be interpreted relative to the molecular weight resolution of the acquisition system. A result such as 1.0004 may represent monodispersity within the practical resolution of the hardware, rather than a physically meaningful distinction from 1. Fractionating a Broad-MWD polymer. Narrow molecular weight standards are often produced by fractionating a broad molecular weight distribution polymer. Preparative SEC is frequently the preferred technique. The process begins by analyzing a small quantity of the broad polymer using an appropriate analytical column. The chromatogram is examined to identify suitable fraction locations. Several elution regions are selected where significant amounts of polymer are present. A larger quantity of the same polymer is then separated under preparative conditions. Fractions are collected at the selected elution positions. Each collected fraction is concentrated and chromatographed again. During this second fractionation, the middle portion of the elution profile is retained, while the leading and trailing portions are discarded. Retaining the central portion reduces contamination from neighboring molecular weight regions. Mn and Mw are then determined for each fraction using suitable independent measurements. The polydispersity is calculated. If the distribution remains too broad, the fraction is chromatographed and divided again. With repeated fractionation, Mn and Mw move closer together. Eventually, the fractions become essentially monodisperse within the precision of the physical measurements. Complete fractionation is rarely practical. Each time, only the middle half of a distribution is retained. Approximately half the material is lost. Repeated fractionation, therefore, reduces the available quantity rapidly. The objective is not necessarily perfect monodispersity, but a suitable compromise between distribution width, material yield, and the intended use of the fractions. Using Chromperfect to select fraction boundaries. Chromperfect can provide the information needed to determine where preparative cuts should be made. Consider a broad polymer with 3 overlapping regions in its molecular weight distribution. Suppose the aim is to divide the material into 7 fractions of approximately equal mass. For a mass-sensitive detector, mass is assumed to be proportional to chromatographic area. The cumulative weight fraction trace shows the proportion of sample mass that has eluted as molecular weight changes. The molecular weights corresponding to 1/7, 2/7, 3/7, and continuing through 6/7 of the cumulative mass can be estimated from an enlarged plot. These molecular weights establish preliminary slice boundaries. A formatted report can then calculate the high and low molecular weight limits, Mn, Mw, polydispersity, weight fraction, and cumulative fraction for each proposed slice. The initial boundaries will not usually produce exactly equal fractions. The slice limits are adjusted iteratively until the weight fractions become acceptably uniform. Once the fractions have similar mass, their calculated Mn, Mw, and polydispersity values can be examined. These values indicate whether the proposed fractions are sufficiently narrow or whether additional fractionation will be necessary. The molecular weight distribution plot therefore supports both equal mass division and assessment of the expected purity of each fraction. Creating an MWD table for a broad standard. Sometimes, suitable narrow molecular weight standards are unavailable. Only an unfractionated broad polymer may be available. Such a polymer can still be used as an SEC standard if its molecular weight distribution can be estimated independently. The preferred information is an MWD table containing several well-spaced entries. An MWD table relates cumulative sample fraction to molecular weight. For example, it may state the molecular weight at which 10%, 20%, and continuing through 90% of the sample mass has eluted. To create such a table, the broad candidate standard is first analyzed using an existing SEC calibration that is believed to be reliable. A formatted report is then generated. The report can calculate the cumulative Mn, Mw, or Mz value corresponding to selected cumulative fractions. Chromperfect report formulas can determine the molecular weight average at which 10% of the mass has eluted, then 20%, 30%, and so on. Mass is assumed to be proportional to area when a suitable mass-sensitive detector is used. The report can display several alternative table series. One series may use cumulative Mn values. Another may use cumulative Mw. Another may use cumulative Mz. The analyst must decide which independently characterized value is appropriate for the intended broad standard calibration. The values should not be accepted merely because the software can calculate them. The source calibration must be suitable. The detector response must be appropriate. The baseline, processing range, and noise treatment must be reliable. The candidate standard must be stable, and its distribution should be broad enough to provide useful points across the calibration range. The resulting cumulative percentages and molecular weights can then be entered into a new SEC calibration file for use with the broad standard integral method. A useful table should contain several entries distributed across the central part of the molecular weight distribution. Values too close to 0 or 100% are vulnerable to detector noise and baseline uncertainty. The extreme tails contain little response, so a small area error can produce a large molecular weight error. Well-spaced intermediate cumulative fractions generally provide more defensible calibration information. The limitation of a derived broad standard table. A molecular weight distribution table derived from SEC is not an independent primary measurement unless the source calibration itself is independently established. If the table is produced using an existing SEC calibration, it inherits the assumptions and errors of that calibration. It may be useful for transferring or reproducing a calibration under similar conditions, but it cannot validate itself. Ideally, the broad standard should be characterized using independent physical measurements or fractions whose molecular weights have been established separately. When an MWD table is derived entirely from an existing chromatographic method, the traceability and limitations of that method must be documented. Conclusion: advanced SEC interpretation requires more than reading one molecular weight value from a report. The molecular weight distribution plot contains several related traces, each applying a different weighting to the molecular population. For ideal distributions, these traces follow regular relationships. The molecular weight markers appear in a predictable order and normally lie at the intersections of the associated fraction traces. Real chromatograms introduce overlapping distributions, curved calibration relationships, detector noise, and non-uniform trace shapes. Nevertheless, the fundamental order and meaning of the traces remain. Axial broadening adds another layer of complexity. The observed chromatogram contains both the genuine molecular weight distribution and spreading introduced by the chromatographic system. Axial correction uses a Gaussian neighboring point model and a column sigma value to estimate corrected molecular weight averages. The correction can provide valuable information, but it depends upon assumptions, is sensitive to noise, and cannot recover information beyond the resolution of the chromatography and acquisition system. Calculated molecular weight calibration plots show how corrected averages vary through the chromatogram. They can reveal local polydispersity, support fraction boundary selection, and help assess whether the selected column sigma value is physically plausible. Chromperfect can also support preparative fractionation by using cumulative weight fraction to divide a broad polymer into approximately equal mass slices. Repeated fractionation can produce narrow standards, although material yield decreases with every stage. Finally, a broad polymer can be characterized using an MWD table that relates cumulative fraction to molecular weight. Such a table can support broad standard calibration, but its reliability depends upon the independence and quality of the measurements used to create it. Together, these advanced tools allow SEC to move beyond a single average molecular weight. They provide a more complete description of the molecular population, the influence of chromatographic broadening, and the practical limits of what the separation and acquisition system can resolve. Thank you for watching. For more chromatography theory, Chromperfect training, technical articles, and product information, please visit www.chromeperfect.com.